All right, now let's talk about the threshold ECDSA key generation. Now remember, we've already done some part of our setup, but at this point we've got to finish the setup. We've got commitments. Everybody has seen everybody else's commitment. They all have an initial random state. And they've all been initialized with this homomorphic encryption scheme. So we've got part of this done. Now, this stuff comes from a paper, okay, and I've put in a link to the paper here in the PDF someplace. But the paper is Threshold Optimal DSA ecDSA Signatures and an Application to Bitcoin Wallet Security by Rosero, Goldfeeder, and Navran. And I've met these guys. They are incredible people. Just incredible in terms of the work that they've done. This paper, okay, has got to be one of the monumental feats of mankind. The thing is loaded with math and it's 42 pages long. It is not a trivial read. It is not trivial to understand it. So as I kind of walk through this, I'm doing kind of the hand-waving version of this. If you want the details, go read the paper. But if you don't get the hand-waving version, it makes the paper understandable at least. So these guys put this together, okay? We have to think about this in terms of a set of signers. And we've got all these signers, and they're all going to be working collectively to get a threshold of these guys to work together to produce the result we want. And in the setup phase, we've shared this homomorphic encryption key. Okay? And I've got to talk a little bit about the notation. The notation in this kind of a thing is pretty standard, but let's look at what we've got out there for notation. When you see one of these y sub i's equal gxi, the y sub I is the ith piece of the public key from the homomorphic encryption. Okay? And the z sub q is the range out there of all the things that we're going to be working in. And you can look at that in two different ways. And the CICD is the range also of the possible values. So when we have some particular value that we're picking it within the range of the elliptic curve. So this is, your 2 to the 256 range. So these are big numbers. And we're going to select a particular random x sub I, which is a random point in this. The random point has to lie on the particular elliptic curve to make this work. And each one of these is going to select a different set of these values. Now, if you think about this in terms of the homomorphic encryption, if I have a whole bunch of values that I've selected around my elliptic curve, and eventually we're going to add these values up, then all we have in the end is an addition operation, and we know on elliptic curves we can do addition. So each person is picking a multiplier, that's the public key, and they're picking a point on the curve. So we're going to go around eventually adding up these points and multipliers, and when we get done, what we have is our end key. So we set it up with the key scheme and the initial values, which gives us our curve. And the end goal is this entire set of things that we're going to add up. Now, because we're working on the encrypted data, all of these additions are based on our knowledge of, with the encrypted data, I can add it up as encrypted values, and at the end, I can get the value I want by decrypting the end result. So, in the middle, the people in the middle don't know what the values really are. They just know if we do the computation correctly, and we don't cheat, we end up with our end result. So we've got it set up, And we'll talk about each player has to now pick, okay, these values. So in our graph world, they've each got their point that they've picked and their number of multipliers that they've picked, which is the y sub I. And they're still computing on their curve. Now, individually, these values aren't going to make any sense because we got to add them together at the end. So they pick these. They each have a piece of a key. Also, we have some little details that x cannot be greater than q, and q is the curve's cardinality when we're picking this. And that guarantees that since it is within the cardinality of the curve, that it is actually a point in the discrete sense of the curves as a instead of a continuous value. And we pick y, and y is g to the power of x. So our elliptic curve pair is this point, and it is this thing. The g is the generator that we've all agreed to in setup, and y is the value that we've picked. So the collective part of this is that once we have picked this, okay, we have a commitment to our piece. So we can say, yeah, I've got the commitment, I've got my number I picked, and I can't lie about it at any point in the future, or it can be checked by everyone. So in terms of network communication, we've got a big thing that we do at the beginning of our network across our nodes to get stuff set up. And then at this point, we have to, once again, but it's a broadcast only, as soon as we've picked this value, we have to commit to it. And we have to have all the nodes send out a broadcast to all the other nodes. But it's not two-way, so it's not too bad a communication, and they now all have everybody's commitment. So every node in our network that's doing this has to track who the sender or who sent it a commitment and what those commitments are. But this means that any node in our network can now later validate that your y sub I that you used is actually correct. Now, this kind of a notation where we have this is often used in math group theory, but there's good reasons to believe that elliptic curve is a group. Dr. Cowles, emeritus professor here, I think has proven that mathematically recently, but for a long time it's been assumed, and he's actually mathematically proven that it matches with math group theory. So, it's kind of cool that has happened, but we've been assuming that it's a group for a long time, and that's now proven. So we've got our commitments, that's our C sub I, and we have the public portion of this and this. So at this point, what do we want to do? We want to distribute the commitments to everybody so that everybody has the proof that will be used later if somebody lies. Now, each player can reveal their piece of this, but only the public portion. Okay? So, each player wants to take their public portion and reveal it. It's going to be needed for validation and the commitment. And our zero knowledge proof on this guarantees that we can't cheat. So within the range, and we can check some things, but we know that it has to be in a certain range, and that the private key portion has to have some properties to it. But basically, we want to distribute this, and when we distribute this, we know that the decrypted portion of alpha is our x, but we're not distributing the decrypted portion, we're only distributing the encrypted portion. So everybody has the encrypted portion of everyone else's key now. Now, the encrypted portion doesn't tell them anything again because it is encrypted. So you have to have the original private key to be able to decrypt it. But since we're working on a system that is homomorphic, we can use the encrypted system to do our calculation. So we're almost there for generating our keys. Okay? The last piece of generating the keys so we've distributed some of the information, and some of this information is actually useful at this point. Okay, we know that there exists in this some sort of a point that is based on collectively all of the x's, and that's the private keys. And we know that it is on the curve, and we know the public key. We know we have a generator for that public key that when it's multiplied by the collective set of all of these public keys is going to give us our end public key. Now, knowing this is enough that we can actually validate that a x exists because it's a zero knowledge proof. We don't know what that value is, but we can actually check it and verify that it is going to exist. And by collectively checking it, we are able to look at this and say, okay, at this point we can check that it is an x and is on the curve, and the encrypted value is on the curve. Now, if anybody in the system cheated, when we do that validation, we're going to find out. And then we can go look for who cheated. But we still don't know what the individual pieces are or what the x that is calculated, the final private key is. We have to do one more step in here to get to that final private key. But the zero knowledge proof stuff can tell us a bunch of things right at that point. So our last step is actually the key generation. Okay? And the key generation means that we're going to end up with our final collective private key. Okay? So the public key we know is the sum of all of the y's from all the nodes, and that's been shared. But now we can take the encrypted public keys, or encrypted private keys, and we can also add those up. So each player can compute those, and each one of these guys, when they compute them, that is actually down here in this step, each one of these guys, when they actually take this and they do the computation on the encrypted values, they can, from that, they can get the original values, because they know that the encrypted sum is equal to the sum of the other values, the non-encrypted, which is equal to alpha, the private key. Now, because we've done this in a threshold fashion, when we have a threshold of these people that can do this, you don't have to wait. If one of the computers fails out of the threshold, it doesn't matter. So we've got some redundancy. But when we do this collectively on the threshold, now we have a public-private key pair. I've also already pointed out that you can use the public key for some things, but now with a key pair that's been generated, that's an ecDSA key pair, we can use this key pair that's collectively generated to do signatures. And the signature algorithm can be done distributed across the network, so nobody has the signature until the end. We can also use this key pair that we've generated at this point to do the Byzantine fault tolerance, where as soon as we have a key pair, we can use that key pair to decrypt something that is the result of this computation that says that this is my new collective state and it is shared across all of these nodes. So before this point in time in step 4, none of them could see this, and at this point in time in step 4, everyone that receives the message and has enough information can suddenly generate the key pair, and that key pair can now be used as proof of the new state of the world. And remember, in the Byzantine fault tolerance, what we're after is everybody can agree at a certain point and nobody can cheat before that point. So this provides us with not just the zero knowledge proof that they didn't cheat, and lie. But it also, because the data is encrypted up to this point, it provides us with an actual encryption proof that they cannot cheat. And they cannot get to the actual new state until this point is achieved. So this has all sorts of unique applications. I think it's interesting that this stuff is got zero knowledge proofs buried in the middle of it, two different kinds. We've got, a distributed network, which means that when you run this, you're probably going to be talking about some point-to-point distributed network, that we're actually doing computations on the encrypted data. The homomorphic is, as far as I'm concerned, just an exciting, wild thing. And at the end, yes, we have something that is a random number generator and useful in other fashions. It's got just all sorts of fun stuff in it that you can play with and use. So if what we're after is that at the end of this, let's say we want the random number, okay? The random number can be used to create a new state for our network. So we don't have to have an individual computer producing this new state. It's a collective computation to get to this new state. And that means there's no point of failure. There's no central authority that's issuing this. If you look at TLS signatures, one of the big problems with TLS cryptography is that we have a central authority in it. Okay, we have VeriSign that ultimately is the central authority, the proof of authority for the network and their keys. And VeriSign has issued signing authority out to a whole bunch of other people out there on the network that can sign. And these other people are not necessarily always trustworthy. Sometimes unintentionally, sometimes intentionally. And Dell managed to lose a pair of signing keys that they actually shipped in software using Microsoft's update. There's an example of, oops, that was bad. Some other people, like the country of Georgia, legally requires that when you sign stuff and you have a private key, that you turn over your private key to the government. So they're intentionally bad. And then sometimes you just have malfeasance with keys. Whenever one of these keys is used and a new key is generated from it, you're supposed to only do that on the authority of the person who owns the key. But one company a year or so back was doing this, okay, and they have since been banned for this, but they were doing this and they were generating test keys without the authority of the person who owns the keys. Now you can use the test keys to sign things, so they could have given those keys away to someone else. They didn't handle their keys properly. And consequently, when people checked and they found out, oh, they're generating additional keys, okay, they could be leaking those. Now, all of these are because we have some sort of central authority. And with this kind of a key generation system, there's no central authority. At the moment when the key is generated, nobody can lie. There is zero knowledge proofs. You can't generate extra keys from this. And it's done in a distributed fashion so that if you have a whole bunch of people working on it, it doesn't matter if one of them lies, because guess what? You have a proof that says, well, you're the one that lied, and you can't do that. And I've got enough redundancy built in the system, and think about 101 nodes, that even if I do have somebody that lies, I can just eliminate their result using the zero knowledge proof, and I can still get the correct result at the end without them. And I can turn around and punish them for lying too. Now, the question is, did they lie intentionally or did they have a network communication failure? So if you're going to actually punish them, you're probably going to have an extra step in here that says, oh, it appears that you may have lied. Okay, give me now a proof that you didn't lie, or I punish you. So if you're going to do that kind of thing, you got to have some extra work in there. You got to have some extra logic that picks that piece out and works on that specific piece. So in and of itself, this isn't quite enough, but that one's a pretty easy to understand. All you have to do is turn around to them and say, okay, it looks like you may have lied. Now turn around and use your key to sign something else and prove to me that you actually have the correct key. and send them a message, see the signature, and say, all right, you didn't lie or you didn't lie, because you can tell from a new signature whether or not they cheated. So there's a way to check them. Now, a key generation scheme like this could be underlying all sorts of network stuff, and with it distributed, you don't have to have any central authority. It's a fully distributed system.